Today we're going to start talking about exponential functions. We've talked about a bunch of different parent functions thus far this year, and now we're going to talk about what happens when my function is exponential. So I'm going to highlight my title, and I'm going to highlight where it says what is an exponential function. So obviously, since I'm talking about exponential functions, I want to know what they are and what it means. So an exponential function is a function, obviously, in the form f of x equals b to the x power. So an exponential function obviously has the word exponent in, so x, my unknown, my variable, is the actual exponent. So it's a function where f of x equals b of b to the x power, where b is a positive real number and x b is a positive real number, and it can be any number other than 1, because if it was anything other than 1, if x was 1, then it would just be a constant line. It would just be anything to the b 1 to the first power, 1 to the second power. It would just be y equals 1 would be that function. So an exponential function is where b is a positive real number other than 1, and x is any real number. Okay? So now I'm going to talk about the difference between exponential growth and exponential decay. So I'm going to highlight the border of my box here just so I know it's significant. So I have exponential growth and exponential decay. So when, let me not write in green. When b, my base, is greater than 1, f of x equals b to the x power represents exponential growth. So when b is greater than 1, so when b is a whole number, 1, 2, 3, 4, anything bigger than 1, it could even be like 1.7. It's going to be an exponential growth. And when b is between 0 and 1 of f of x equals b to the x power, it's going to represent exponential decay, which means something is decaying, is declining exponentially. So what this means is that when b is a fraction, it's going to be a exponential decay, and when b is greater than 1, it's going to be a exponential growth. So if we go down and we look at these examples, it says tell whether each function represents an exponential growth or decay. So if I look at number 1, f of x equals 3 to the x power, look at b. b equals 3. So is that going to be a growth or is that going to be a decay? Well, it's going to be a growth because it's greater than 1. If I look at number 2, f of x equals 2/3 to the x power. So 2/3 to the x power, so b is 2/3. So since b is less than 1, it's going to be an exponential decay. So go ahead and pause this video and try 3 and 4 on your own, and then unpause this video and we'll go over the answers. If I look at number 3, my b is 3/2, which equals 1.5, which is greater than 1, so this would be a growth. And if I look at number 4, I have two numbers. I have 3 and I have 1/2. But to determine whether or not it's an exponential growth or an exponential decay, it's just the base of the exponential function. So the base is at just 1/2, so it would be a decay. So let's go ahead and keep going. We're now going to talk about graphing exponential functions. And I'm going to zoom in here. So if we talk about graphing exponential functions, whenever we learned how to graph anything in the past, we always started out by making a table. So I'm going to do that exact same thing here. I'm going to make a table of x values and y values. And I'm going to plug in, I'm going to pick any values I want for x. So the common values are -2, -1, 0, 1, and 2. You could pick any values that you want, but these usually are the easiest. So now all I got to do is plug these values in for x. So if I plug these values in for x, let's just do 0 first because everybody likes 0 the best. If I plug in 2 to the 0 power, what's that going to equal? Well, that's going to equal 1. What if I plug in 2 to the first power? 2 to the first power, well, that's just going to be 2. And if I plug in 2 to x, 2 squared is going to be 4. So now let's talk about negatives. If I plug in 2 to the negative first power, because I'm plugging in -1 for x, notice this is a negative exponent. Remember, negative exponents turn things into fractions. So 2 to the -1 is the same thing as 1/2. If I can write, I would write 1/2. 2 to the negative second power is the same thing as putting 2 on the bottom. So 2 squared goes on the bottom, 1 goes on the top. That's cleaned up to 1/4. So -2 is equal to 1/4. So now these all just make ordered pairs. So now I'm just going to graph it. So I'm going to graph -2, 1/4. I'm going to graph -1, 1/2. I'm going to graph 0, 1. And I'm going to graph 1, 2. And I'm going to graph 2, 4. And notice my function gets super close to this, which means there's an asymptote here. And then I'm just going to connect my dots to get my graph. So notice that this was getting extremely closer down here. This was getting extremely closer to 0. But when you start plugging in values, if I were to plug in 2 to the -7th power, that's going to be 1 over 2 to the 7th power, which is a number. And that's going to be greater than 0, which is why I have this asymptote right here. Exponential functions, if you also want to just memorize it, always have an asymptote at y equals 0. So if I come down here to fill in this information, so let me zoom out a little bit so we can see it all. All right. So my domain, what would my domain be? Well, it's all real numbers. It's going from -infinity to +infinity. How about my range? The lowest value it's ever going to get is 0, but it's never going to approach 0, which is why it's a parenthesis. And the highest it's going to get is infinity. My y-intercept. So I can look on my graph. My y-intercept I know is right there, which is 0, 1. If I didn't have a graph easily to be able to determine that, I could have just plugged in 0 for x and solved. Asymptotes, I said, was at y equals 0. That's always the case, so you can go ahead and memorize it. There are obviously certain instances, which when we get on the next page, we'll talk about how that can change. So let's now talk about end behavior. When x is going to -infinity, where's y approaching? Well, when x is going to -infinity, y is getting super close to that asymptote, which is 0. And when x is going to +infinity, where's y going? It's also going to +infinity. So now if I'm looking at this, let's first go back to the equation. Looking at this equation, was this an exponential growth or was this exponential decay? Well, this was growth because b was greater than 1. So, because it's growth, that chances means it's increasing and not decreasing. If you look at this function, it's also from left to right increasing. So it's increasing from negative infinity to positive infinity, and it's never decreasing. All right, so now let's go ahead and let's look at this one. I'll zoom into graph and then I'll zoom out. So again, I'm going to make my table of values, my x value, my y value. I'm going to pick the same x values because it makes it easier. I now always start with 0 until I get good at this. Soon you won't need to draw this table, but if you have to draw this table every time to make sure, that's totally cool. So if I plug in 0, 1/2 to the 0 power is 1. If I plug in 1 for x, 1/2 to the first power is 1/2. And if I plug in 2 for x, 1/2, don't know what I just did, 1/2 to the second power is equal to 1/4. So now let's do negative exponents. 1/2 to the negative first power. So that just means these two are going to flip locations to be 2/1, which just makes 2. 1/2 to the negative second power. These two flip locations, so it's 2/1, and then I have to square it, which will be 4/1, which just makes 4. So now I'm just going to go ahead and I'm going to graph this. So I have -2 to the 4th power. I have -1, no, I was saying that wrong. I have -2, 4 as one ordered pair. I have -1, 2, it's another ordered pair. I have 0, 1. I have 1, 1/2. And I have 2, 1/4. So again, notice it looks like it's approaching 0. And I'm going to go ahead and I'm going to draw my function. If I look at this equation, is this equation exponential growth or exponential decay? Well, it's exponential decay because b is less than 1. If you look at these two equations, notice this one's going up and this one's going down. Because that's what it means to be growth, it's going to be increasing, and for it to be decaying, to be declining, it's going to be going down. So now let's go ahead and fill out this information. My domain is still all real numbers, negative infinity to positive infinity. My range, my lowest value is 0, but it's never going to be 0, and then it's going to infinity. My y-intercept is 0, 1. My asymptote is y equals 0. My end behavior, as x is going to negative infinity, where's y going? So negative infinity is here. Where's your y values going? To positive infinity. And as f of x is going to positive infinity, where's y approaching? 0. So now it can either increase or it can decrease. Which one do you think it's going to do? It's decreasing. It's not increasing. It's also decay, which means you know it's decreasing. But it's decreasing from negative infinity to infinity. Exponential models can either increase or decrease. Go ahead and flip your paper. So now we want to start talking about transformations with these fun things. So all of our transformation properties that we learned back in Unit 2 apply for this one. So if I look at this first example, 2 to the x plus 3 minus 5, what transformations is going on in this problem? Well, I have a minus 5, which means I know I'm going down 5. And I have this plus 3 next to x, which means I'm going left 3. So I'm going left 3, down 5. If I look at number 2, I know this plus 1 tells me I'm going up 1. What does this 2 next to x mean? Well, it means it's a horizontal compression of 1/2. Look at number 3. Number 3, I have 2 to the x minus 3. So what is this minus 3 telling me? It's going right 3. This 2 in the equation does nothing because this 2 is what b is. That's the base. That's what makes this exponential function. So this 2 isn't part of the transformation. It's part of the equation. So I want you to go ahead and pause this video, and I want you to do 4, 5, and 6 on your own, and then I want you to unpause it, and I'll go over the answers. So if I look at number 4 has a 4 on the outside, which means it has a vertical stretch of 4. If I look at number 5, my x is negative. So when x is negative, it means it reflects over y. Here I have a negative away from x, which means I reflect over x. And this 2 also tells me it's a vertical stretch by 2. So now I want to go ahead and I want to start graphing these functions. So I want to describe the transformation. So this is going to go right 2. So I'm going to go to the right 2, and I'm going to put just like a little cross there. And if I can write that a little prettier. This is now my makeshift origin, which means my asymptote still goes like this. But I'm using the parent function of just what it originally looked like. Parent function is f of x 3 to the x. So I'm just graphing 3 to the x, but now I'm graphing it as if this was my origin. So I'm still going to make my table, specifically if you don't know what to do. So x and y, -2, -1, 0, 1, and 2. If I plug in 0, 3 to the 0 is 1. If I plug in 1, 3 to the 1 is 3. If I plug in 2, 3 squared is 9. If I plug in -1, 3 to the -1 is 1/3. And if I plug in -2, -3 to the -2nd power is 1/9. Make sure if you don't understand how I'm getting this table, you're asking questions. So now I'm just going to apply these points as if this little t right here were my origin. So because it says 0th 1, I'm going to go at my origin that I made, 0, 1, and I'm going to plot that point right there. I'm now going to go 1, 3, so from my makeshift origin, I'm going to go over 1, up 3, and I'm going to plot that point. If I could go over 2, up 9, I would, but I'm not going to because I'll go off my grid. But I am going to go -1, so from my makeshift origin, I'm going to go to the left 1, and I'm going to go up 1/3, and I'm going to plot a point. And then I'm going to go over 2, and I'm going to go up 1/9, and I'm going to plot a point. And I'm going to connect my dots to get my exponential growth function. So now I want to go ahead and fill out this bottom information. The domain is -infinity to +infinity. My range is 0 to infinity. My y-intercept. So now looking at this actual function, I want to find what that y-intercept is right there. So you have a bunch of different ways you can do it. You can plug in 0 to the original function to find it. Or you can say, okay, this point here came from going to the left 2 from my origin. So that would be -2. So 1/9 is my y value of that. But if you don't like doing it that way, you can just do 3 to the 0 minus 2, which, because I'm just plugging 0 in for x, which is 3 to the -2nd power, which is 1/9. So I have 0, 1/9. My asymptote is at y equals 0. When f of x is going to -infinity, where's y going? To 0. When when x is going to +infinity, where's y going? To infinity. And is this function increasing or is this function decreasing? Well, it's increasing from -infinity to infinity, and it's not decreasing because it's exponential growth. If I go ahead and I look at this next one, This one tells me I'm going to go up 2. So I'm going to go up 2 and I'm going to draw my makeshift origin. That's now my makeshift origin. I'm now going to make my table if I can't do this in my head. And I'm going to plug in 0. And I'm just using my parent function, f of x equals 1/3 x, to get my table. So if I plug in 0, I get 1. If I plug in 1, 1/3 to the first power is 1/3. If I plug in 2 for x, 1/3 squared is 1/9. If I plug in a negative 1, 1/3 to the negative first power, I just flip it, so it's 3. 1/3 to the negative second power, I would flip it, and then I would square it, so it would be 9/1, which is just 9. So now, from this makeshift origin that I made, I'm going to draw my horizontal asymptote. And from this makeshift origin, I'm just pretending this is now 0, 0, and I'm plotting these points. So I have -1, 3, which goes up here. I have 0, 1. I have 1, 1/3. And I have 2, 1/9. So now if I go ahead and I look at this, my domain is -infinity to +infinity. And my range is 2 to infinity. My y-intercept, so where does this touch my y-axis, is at 0, 3. If I couldn't tell, I would just plug in 0 to my original function and solve. Notice here my horizontal asymptote is not at y equals 0. It's been shifted vertically up. So my asymptote is now y equals 2. My end behavior, as x goes to -infinity, f of x goes to infinity. And as x goes to infinity, f of x goes to 2. So looking at this picture, is it increasing or is it decreasing? Well, it's decreasing because it's going down, so it's not increasing. And it's decreasing from -infinity to infinity. So let's go ahead and let's do this next one. Alright, so if I look at this next one, 4 to the -x power, so I'm not shifting my origin, so my origin isn't staying, in fact, at the original origin. But this -x means I'm flipping it over the y-axis. So I'm using the parent function, f of x equals 4 to the x. We're going to try not writing the table. I'm going to try doing the values in my head. So if I plug in 0 for x, I get 1. So it'll be 0, 1. And I can't flip that over the y-axis because it's on the y-axis. So now I'm going to plug in 1 for x. 4 to the first power is 4. So I should go over 1, up 1, 2, 3, 4. But because I have to flip it over the y-axis, I'm going to put it over here. 4 to the second power would be 16. That's going to go off my grid. So what if I do 4 to the negative first power? That would just be flipped to 1 over 4. So I would go over 1, up a quarter. But because I'm flipping it over the y-axis, I'm going to graph it there. And then 4 to the negative second power is 1 over 16. So it looks something like this. So my domain is -infinity to +infinity. My range is 0 to infinity. My y-intercept is 0, 1. My asymptote is at y equals 0. When x is going to -infinity, where's y going? It's going to +infinity. And when x is going to infinity, where's y going? To 0. Looking at this function, is it increasing or is it decreasing? It's decreasing. negative infinity to infinity. So I want you to go ahead and pause this video, and I want you to try this one on your own, and then you can unpause this video and the answer will be on the board for you to check. So go ahead and pause and then unpause once you've made an attempt. So the answer to number 2 is on the board, or on your screen, I guess I should say. Go ahead and check your work, and if you have questions, make sure you ask me. When you're good, go ahead and flip your paper. So same thing with 3 and 2. Clearly I can't count. 3 and 4. I want you to go ahead and pause this video. I want you to try these two on your own, and then you can unpause this video and your answers will be on the board. So the answers are on the screen, so if you have any questions, make sure that you come and ask me. So we're now going to go ahead and we're going to move on to exponential growth and exponential decay models. So I'm going to go ahead again and highlight the border of my box. And let's check it out. So an exponential growth or decay model is represented by A equals P times the quantity of 1 plus or minus R to the T power. So it's 1 plus R if it's a growth model, and it's 1 minus R if it's a decay model. So in this equation, A is the amount after T years, and R is the rate of growth or decay, and P is the initial amount. So P is the initial amount, R is the rate that it's growing, and T is how long it's growing, how long. So if I look at example 1, it says, suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will the account be after 5 years? So I started out with putting how much money in my account? $500. So then it pays 1.35 annual interest. Is that growing interest or decaying interest? Well, interest is growing. So this is going to be 1 plus R is a decimal. So I have to convert this percent to decimal. So I have to move my decimal 2 places. So it's 0.035 raised to T, which is the time. So T, it takes 5 years. So 5 would be my exponent. This all equals the amount afterwards. So if I type all of this into my calculator and I hit enter, the amount that I am left with is $593.84. So what this is telling me is that in 5 years, if this was my annual interest and I started out with $500, I would end up with $593.84. If I look at the next one, it says a new school district is experiencing an annual growth rate of 9.5%. The school population is now 5,600 students. What will be the approximate predicted population 5 years from now? So I see the percent. I see my percent. I know that's R. The school population is now 5,600. So that's where I'm starting. So that's P. It's my initial. It's growth. So I know it's 1 plus R. What will it approximately be in 5 years? That's T. So plug it in. A equals P, which is my initial start, 5,600, times the quantity of 1 plus, because it's growth, of 9.5%. To turn that into decimals, it's 0.095, raised to the T years, so 5 years. So I would type all of that in my calculator, hit enter. So I get a decimal. So obviously you can't have point something of a student, so I'd round to the nearest whole number, which is 8,816 students. All right, let's try one more together. The rate in the number of reported cases of robbery is dropping at about 7% per year in a given region of the country. The number of cases reported this year was about 156,000. The number continues to drop at this rate. What will be the predicted number of cases 3 years from now? So I saw percent, so I know that's R. Number of cases report, I see the word dropping, so I know it's a decay. The number of cases reported was 156,000. That's P. And at this rate, what will be the predicted case in 3 years? That's T. So I have A equals my initial amount, which is 156,000, times the quantity of 1 minus, because it's dropping, so it's decay, of 0.07 to the third power. So when I type this in my calculator and I hit enter, I again get a decimal. So I can't have points certain number of cases, so I round. So I have A equals 125,480 cases. So go ahead and pause this video and try number 4 on your own. When you finish, unpause and you will get, your answer will be on the board. So hopefully you see your answer. When you're good to go ahead and flip your paper. We have one last topic to talk about, and that's called compound interest. Compound interest is the interest paid on an initial investment called the principal and on previously earned interest. So this is my formula. So I have a bunch of different variables. P is the initial. Oops, let me not write in highlighter. That would not end well. P is the initial principal deposited. So it's the initial amount. N is the number of times per year. A is the amount after T years. T is number of years. And R is annual interest rate. So if I look at this formula, it does look different than exponential growth and decay. However, it just is another way. It's when when I am calculating compound interest. So if I go ahead and I look at this example, it says find the balance of the account. I deposited $6,500 into my account that pays 2.35 annual interest. Find the balance after 3 years if the interest is compounded annually. So if I look at this picture, if I look at this problem, when I deposit $6,500, that's P. That's my initial amount. It pays 2.35% annual interest. That's R because that's my annual interest rate. The balance after 3 years, so I see the word 3 years. I know that's T. So if I look up here in this problem, all I need left is N. If I go down here and I think about N is the number of times per year. So A says the interest is compounded annually. So when it's compounded annually, how many times a year is that? Well, that's 1 time a year. So I have all my variables. Let's now plug it in. A equals P, which is my initial amount, which is $6,500, times the quantity of 1 plus R, which is my annual interest rate. I can't type in decimals, I have to convert it to a fraction. So it's 0.0235 all over n. We said n was 1. Raised to the n times t power. N is 1, t is 3. So if I just clean this up, it's 6,500 times 1 plus 0.0235 over 1, which is just 0.0235, all raised to the 3 times 1 power, which is 3. So I'm now typing all of that in my calculator and hitting enter. The A, which is the amount after t years, is $6,969.10. If I go to B, it says, what if the interest was compounded monthly? So P, R, and T are all the same, but now N is changing to monthly. So N is the number of times per year. So if it's monthly, how many times a year is that? Well, there's 12 months in a year, so 12 times. So I'm going to use the same formula. A equals 6,500, because that's P, times the quantity of 1 plus my percent, which is 0.0235, all over n, which this time is 12, raised to the n times t power. So that'd be 12 times 3 power, which is 36. I'd type that in my calculator, and I would get 6,974.31. So $6,974.31 if interest was compounded monthly. So go ahead and try this last one on your own when it's compounded daily. If it's compounded daily, how many times a year does that happen? 365, because there's 365 days in a year. So go ahead and try this one, and then unpause this video to get your answer. So my answer is $6,974.77. So notice if interest is compounded monthly versus daily, it's not that much different interest rate, but it does save you about $5 if it was annually. So when you're finished, you can go ahead and move on.